All right, well, it's time to do some practice with derivatives and trigonometric functions. And it's good because now we're expanding our repertoire of things we can do. So we're going to do a lot of problems which have been similar to the things we've done already, but now we're going to throw the trig functions into the mix. As always, you should do as much of these problems as you can on your own before seeing the solutions. And even as you're watching the solutions, if you haven't quite finished yet, use that pause button and only get to where you're stuck, get unstuck, and then get back to work. And remember, you need to do the work because that's how you're going to build up your beautiful monument to calculus. All right, well, let's begin. So our first problem, suppose we have our function is sine of x. We want to find dy dx, which means the first derivative, d squared y dx squared, the second derivative, okay, then third derivative, fourth derivative, fifth derivative, and the 107th derivative. Well, you might be thinking, are we really going to take 107 derivatives? And you probably have guessed the answer is no. We're going to do something a little bit better. All right, which is we're going to figure out what it should be. All right, so how do we do that? Well, let's start with our function, y equals sine of x. We write down our derivative, dy dx. Now, the derivative of sine, we know that. We just learned it. It's cosine. Now, the second derivative, what would that be? Well, that's the derivative of cosine, and we know the derivative of cosine is negative sine. That looks familiar. So, third derivative. What do we see there? Well, the negative is like a constant. It's like -1. So it's going to be negative of what the derivative of sine is. So that's negative cosine. Fourth derivative, what would that be? Well, the fourth derivative is what? The negative is a constant times the derivative of the cosine. So it's like negative sine, but of course we just write that as sine. And now you might be saying, we've definitely seen that before. And what do we mean? Well, look, if I start with the sine and I take 4 derivatives, I'm back to sine again. So it seems to be the case, because it is the case, that taking 4 derivatives returns us back to where we started if I'm working with the function sine x. All right, so what does that mean? Well, that means taking the 5th derivative is really the same as taking the first derivative, because remember, we've reset. And so if we're back to sine, the derivative of sine is cosine. Okay, so now we see there's going to be a definite pattern. We're going to be going sine, cosine, negative cosine, back to sine, cosine, negative cosine, sine, cosine, negative cosine, da 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 da. So every 4 derivatives it's like we're starting all over again. So we think to ourselves, okay, if I have 107, how can I think of 107? Well, that's really 4, and let's divide 107 by 4. Well, it's not quite divisible by 4, right? But if you take 4 times 26, that would be 104 plus 3 more. So here's the thing. We know that every time we take 4 steps, we get back to where we start. So we're going to go through 26 cycles where we're going through the sine, cosine, negative cosine, sine, cosine, negative cosine. And after we've gone through 26 cycles, then we're going to be like, and then 3 more steps. Okay, so what does that tell us? Well, it tells us if I want to know what the 107th derivative is, I can say all I need to figure out, and this is true in general, is say, okay, how many times did I go through steps of 4? And then after I've done that, how many more steps did I take? Well, the answer is I took 1, 2, 3 more steps. So it's the same as if I had taken the third derivative. And therefore, the 107th derivative is negative cosine x. And there you go. All right, good, good. See, we didn't have to take a lot of derivatives. What we had to do was find a pattern. And pattern finding is a very useful and important tool. You really want to do that. In fact, a lot of math and solving problems comes down to saying, I've seen something like this before. I know how this pattern works, and let me use what I've done before. All right. So our next problem, find the derivative of sine of 2x. Now you're probably thinking, hey, there's a simple rule for that. Well, there is, but we don't know it yet. So let's suppose we didn't know it. We say, well, how can we do the derivative of sine of 2x? Well, the derivative of sine of 2x is the same as taking the derivative of 2 sine x cosine x, because there's this nice thing called the double angle identity, which allows me to replace sine of 2x by this relationship, 2 times sine times cosine. So we can say, let's take that derivative. Now the nice thing is, see, the reason why sine of 2x is not trivial right now is how do we handle the 2? See, that's a little bit different. We know how to handle just x on the inside, that's our rule, but we don't know how to handle when there's a 2 on the inside. So what we want to do is find a way to say, can I move the 2 out? And that's why we use our trig identities. So there's so many trig identities. It's, at the same time, wonderful and beautiful and makes trigonometry very flexible, but also very challenging because you're like, there's so many things to choose from. I have this huge buffet of options as far as what functions and identities I can use. And so it's always not clear what to do. But they told us, and so that's good to know. And by the way, sine of 2x, it's one of the 6 important trigonometric identities. So it's good for you to know this one. So now the constant, I can just treat that as a constant. Don't need to worry. And I have a product rule. So if I do the product rule, so I have the 2, derivative of sine, cosine, and then leave the cosine alone, cosine, and then plus 2, then times sine, right, because it's the derivative of the first times the second plus the first times the derivative of the second, which is negative sine. So if I pull out a 2, what do we have? We have cosine squared x minus sine squared x. Now, thinking back to your trig identities, you might be like, oh, is that 1? Oh, careful, careful, careful. Cosine squared plus sine squared is 1. Cosine squared minus sine squared is not 1. But it is something. What is it? A great chance to review our trig identities. Cosine squared minus sine squared is actually cosine 2x. It's the double angle formula for cosine. And so what we end up with is 2 cosine of 2x. So it's kind of interesting. See, we took the derivative of sine, and normally the derivative of just sine is cosine. Well, again, that's what happened here. But when we had this 2x, somehow there's a 2 that showed up. That's a, I feel like something's going on here. I feel like something's going on here. Well, I hope we'll find out. We'll find out. All right. Good. Now, our next problem. A 10-foot ladder leans against a wall, where theta is the angle between the ladder and the wall. And suppose that x is the distance from the bottom of the ladder to the wall. Find the rate of change of x with respect to theta for an arbitrary value of theta. Now, we see a couple of things. So here, of course, we see things like rate of change, and that means find a derivative. So that's, we're learning our code. And see here, next thing we see of x with respect to theta. So that's saying find dx d theta. How is x changing with respect to theta? So we're saying, aha, we want to find dx d theta. So to do this, we want to write x equals something with theta. And if we can write that expression, then we can say, all right, if we can get to this stage, then we can take a derivative, and then we'll be done. Okay, well, how do we do it? Well, we have a description. Probably a useful thing is to draw a picture. and pictures can be very, very helpful when we're doing it. So you might start saying, okay, well, I got to start drawing pictures. So you start drawing a ladder, and then here's another part of the ladder, and there's the rungs going across. And at this stage, you're like, wow, these problems are going to take a long time. And, just the picture, okay, here's the ladder. Of course, there's the wall, and we have this coming up. And, all right, so, that seems to be a lot of work. And ladders are among the things that can be drawn relatively easy. How are we going to do these problems? Well, the thing is, we want to get away from pictures which are trying to be somewhat accurate in the drawing. What we want to do is just simplify our drawing. Okay, so instead of having something complicated, when we draw our pictures, what we'll do is we'll say, look, here's the wall. Here's the floor. Here's the ladder. So that's how we're going to draw our pictures. We're going to make them very, very simple. And now we can really get the full flavor of what's happening. We start figuring things out. Okay, so first off, we see there's this number here hidden as a word. Normally it's nice for them if they put actual numbers, because then our eyes get drawn to it. But okay, so 10-foot ladder. So that means this is 10. And then we have theta is the angle between the ladder and the wall. So here's the ladder, here's the wall. So the angle theta goes here. X is the distance from the bottom of the ladder to the wall. So this part downstairs, this part is where X is. So we have, and of course, let's assume that this is built to code so that, the floor and the wall made a nice right angle. And now we say, all right, I want to find some relationship that involves X and theta. Well, I have a good triangle. In fact, it's the right triangle. And there's a theta, an X, and a 10. In terms of the relationships, I see that X is the opposite to theta. 10 is the hypotenuse. So I think opposite and hypotenuse, well, that tells me there's a sine theta. Sine of theta is opposite over hypotenuse. Or we get X equals 10 sine theta. Now we're in good shape. We have our X equals something with theta. We know we're after dx d theta, so we take our derivative. So taking our derivative, dx d theta would be 10. Derivative of sine theta is cosine theta. And that's our answer. So as we vary theta, this is how the x will change. And of course, it depends on your theta. And depending upon theta, it might change a little bit, it might change a lot, relatively speaking. So, okay, good, good. Progress. All right, on to our next problem. So, determine a and b so that f of x will have a derivative at x equals 0, where f of x is defined piecewise by 3 tangent x minus 2 secant x if we're below 0, and a e to the 2x plus bx if we're above 0. So this is a piecewise function. And now we ask, okay, what's happening? Well, what's happening is, of course, we have one behavior on the left, another behavior on the right, and what we do is we're trying to glue the behaviors in such a way that it's a smooth transition from one side to the other, smooth being differentiable. Now, there's a couple things that have to happen. We have to make sure they line up. See, if they're coming in at different heights, it won't work. The other thing is we have to make sure that when we look at this relative slopes, they don't look like this. There's not a no. We got to make sure that the slopes match. All right. So, how do we do this? Well, implicitly, there's a limit involved in this process, but let's get to the point where we just sort of walk through and think of it heuristically. So, we're going to look at the function, and we're also needing to look at the derivative. Now, when you have a piecewise function, you also get a piecewise derivative with a caveat. Where they glue together, you don't know what's happening. So just don't do the place where it glues. So let's take our derivatives. Derivative of 3 times tangent. Well, 3 is a constant. Derivative of tangent is secant squared. Then minus derivative of secant. Well, the derivative of secant is secant tangent. And that's going to hold where I'm not gluing. So if this is my function for x less than 0, this is my derivative for x less than 0. Now I come to a e to the 2x plus bx. Well, we've figured out how to take the derivative of e to the 2x, so that brought down to 2. So 2a e to the 2x. We did that before in some of our practice. You've been doing the practice, right? Well, of course you have. You're a great student. Thank you for working so hard. The derivative of b times x. b is a constant, so b is a parameter to be chosen. So it's a constant times x, so you end up with plus b. And now that's if, see, not greater than or equal to 0 is for greater than 0. Because at the gluing point, we don't know yet. That's what we're trying to figure out. So here's the moral. So first off, we have to have the two functions have to match at the gluing point. And when I say the functions, the piecewise function parts. So how do we do that? Well, officially, we say, well, we take a limit and then we figure it out. Now, if we're dealing with functions which are continuous and we can plug it in, we can sort of skip the step. If the limit is tricky, we got to dig into it. But look, we can plug 0 in because these are continuous functions and they're defined at 0. When you plug in 0, what do you get? You get 3 times 0 minus 2 times secant of 0. Ah, see, tangent of 0, I said it was 0, and you're like, yeah. Do you remember what secant of 0 is? How about cosine of 0? That you might know. Cosine of 0 is 1. Secant, you flip it over, so it's still 1. So on the left, we're going to end up with, write it down, 3 times 0 minus 2 times 1, which is also known as negative 2. On the right, what do we get? Well, we're going to get a e to the 0 plus b times 0, also known as b times 0 is 0, e to the 0 is 1, a. And therefore, we have that a has to equal negative 2. Now, hidden in the details are the fact that we really have to say there's a limit going on. So, in essence, this left here, this is the limit as x approaches 0 from below of f of x, and from the right, this is the limit as x approaches 0 from above of f of x. All right, now that's half of it, and good news, we know what a is. A is negative 2, so we'll keep that in mind. So here's our answers. A is negative 2, B is something. I hope I have enough space. Oh, I hope I'm not going to regret the size of that box. Okay, now the next part is that the derivatives also have to match at our gluing point. Okay, so let's see what that means. So take our derivatives and again plug in 0 because 0 is our gluing point. So 3 secant squared of 0, well, that would be 3 times 1 minus 2 times 1 times 0. 2 times 1 times 0. Well, if you clean that up, that's 3. Okay, this is the left. Equals on the right. Well, plug in 0. 2 times a times e to the 0, which is 2a. So we get 2a and then plus b. Plus b. And this is equal to, well, I know what a is. A is negative 4. So that's negative 4 plus b. This is the right. Now again, really what's happening here when we say the left, this is really the limit as x goes to 0 from below of the derivative f prime of x. And here, this is our limit as x goes to 0 from above of f prime of x. But now we can see, aha, we need 3 to be negative 4 plus b. Well, we add 4 to both sides, and we come to the conclusion that b should be 7, and we're done. Woohoo! Yeah, we made it! We made it! We got it to work! Nice, nice. I like it when we get an answer, and that especially I like it when the numbers are reasonable. After all, shouldn't math be reasonable? One would hope. One would hope. All right, our next problem. So, find, in our notation here, d squared d theta squared says 2 derivatives with respect to theta of sine theta over 1 plus cosine theta. So we have this expression, and we're going to take the derivative of this expression twice. Okay, well, of course, we do it by starting by taking the derivative once. So let's take, again, we can think of this as the derivative of sine of theta over 1 plus cosine of theta. So we begin. So this is the derivative of, now, what's the rule we use here? Well, we have a function on the top and a function on the bottom, so we're going to use quotient rule. Okay, so quotient rule says we're going to take the bottom times the derivative of the top, derivative of sine is cosine, minus the top, and what's the top? Well, sine, times the derivative of the bottom. Okay, derivative of 1 is 0, because it's a constant. Derivative of cosine is negative sine. All of that, divide that by the bottom squared. And there we go. Good, good. Now, what happens next? Well, we could jump right into taking this derivative, but why is that a bad idea? Well, it's a complicated expression. See, whenever you have something and you get to a point, you're like, well, I need to do something with this expression again. What you should ask yourself is, can I simplify what I have? If the answer to that question is yes, you should be simplifying. So, can we simplify this? I think we probably can. We haven't even tried, so we should at least try before we do it. Remember, the goal is, if you're continuing to do something with an expression, make it as simple as possible, because we love ourselves. We want to take care of ourselves and make sure that we are putting ourselves in the best situation to succeed. So we proceed. So what do we have? Well, if we multiplied that cosine through, that would be cosine plus cosine squared. Then minus minus makes plus sine squared over 1 plus cosine squared downstairs. But now we're like, hey, wait a second. Cosine squared plus sine squared. That's an identity. That's one of the best trig identities. In fact, I would say it's the #1 trig identity. So we can replace that. So that's really the derivative of cosine of theta plus 1. And of course, downstairs you have 1 plus cosine theta squared. All right, how we finish simplifying? Can we do any more? We can do one more thing. You see that cosine theta plus 1, it doesn't matter what order we write things. So cosine theta plus 1 is the same as 1 plus cosine theta. So I can switch the order, and the point here is I can get a cancellation. So this is the same as 1 over 1 plus cosine theta. Nice. See, if I had to choose between these two derivatives, I would definitely want to choose taking this derivative because it's a simpler expression. Indeed, look at it. Theta only shows up in one place. That's about as simple as you could possibly hope for. Now, you can think of this as a quotient rule, or if you like memorizing lots of rules, you can think of this as a reciprocal rule. So if you think of it as a reciprocal rule, the way you do that, and by the way, the reciprocal rule you can think of as a special case of the quotient rule. So if you were to do the quotient rule, you take the bottom times the derivative of the top is 0, because the derivative of the top is 0. So you end up with minus the derivative of the bottom. Well, derivative of 1 plus cosine is what? Well, it's minus sine theta all over the bottom squared. So minus minus sine makes us a plus sine theta. Divide that by 1 plus cosine theta squared. And there you go. It's amazing. See, it's surprisingly close to our original guess. Or sorry, our original function. It was sine over 1 plus cosine. We end up with sine over 1 plus cosine squared. That's kind of cool. Who would have thought? Well, that's why we did the work. Because maybe we wouldn't have thought that. So it's nice to be able to do the work and get the answer. All right, one last problem. Whew. All right. Suppose that we have a way to control a particle. Maybe we are working for a particle collider. So we have like magnetic fields or something where we can whoosh, guide a particle. All right. So we have a way to control a particle so that its position at a given time t is given by some function, a times t times sine t plus b times cosine t. And a and b, that's how we can control it. We can control those values, a and b. So we need to ensure that its velocity at time pi halves is 2 and that its acceleration at time pi is 5. So that's what we need. Now notice here, what do we have? We really have one condition here. So this is our first condition and this is our second condition. So we have two requirements, if you will. Now, how many things do we get to set? We have two things we get to set. We get to set A and B. And so for every requirement, we should have 1 degree of freedom. So you sometimes will hear degrees of freedom. That's how many choices that get to be made. So we get to make 2 choices. So it's reasonable for us to be told 2 things have to be satisfied. All right, that should determine what A and B are. So after we figure out what A and B are from these 2 conditions or requirements, then the question becomes, well, what would be the position of the particle at time pi fourths? All right, so let's dig into it. So we have our function, s of t is a t sine of t plus b times cosine of t. All right, now we need to talk about velocity. How do we find velocity? Velocity is about how we change our position, and so that's our derivative, s prime of t. What rule do we need for t times sine t? Product rule, because we have 2 things multiplying. So the a is a constant, so the derivative of the first will be, think of the derivative of t as 1, so the a constant comes along, a sine t, then plus a t times the derivative of sine, because the derivative of the first times the second plus the first times the derivative of the second is cosine. Then plus b times derivative of cosine. Derivative of cosine is, well, negative sine. All right, there we go. There we go. Okay, now that's round 1. If we wanted to, we could actually combine those together. See, they both have sine t. So we could write this as, for instance, a minus b times sine t, then plus at times cosine t. It may or may not help us. At the very least, it's a little bit shorter to take the next derivative. Because we're going to need the next derivative, that's where the word acceleration comes into play. Acceleration is the second derivative. So we have the second derivative, s double prime of t. Okay, so a minus b is a constant, then that's times the derivative of sine, which is cosine, plus, next, product rule. So derivative of the first is a times the second, so a cosine t, plus a times t times the derivative of cosine. Derivative of cosine is negative sine. And now we can clean this up. Well, why? Well, we see an a minus b cosine t and a cosine t. So this becomes 2a minus b times cosine t, and then a minus at sine of t. All right, so we found the velocity, we found the acceleration. Now we can start figuring out what a and b need to be. So we're told that at time pi halves, the velocity is 2. See, velocity at time pi halves, so s prime of pi halves needs to equal 2. E is equals 2. Okay, so plug in pi halves. Now, what's true about sine of pi halves? Sine of pi halves is 1. So we're going to get a minus b. Cosine pi halves is 0. Goes away. So that's it. A minus b. Yeah, that's it. So now this is one condition. A minus b has to equal 2. All right, well, now let's dig in and get another condition. So that's our second condition. The acceleration at pi, so s double prime at pi, needs to be 5, equals 5. So now we'll plug pi in. Now, what happens? What is cosine of pi? And be careful, cosine of pi. Think of the unit circle. So when we're at pi, we're halfway around. So this is where pi would be. Now, the cosine is the x-coordinate, so that is -1. So that says 5 is equal to 2a minus b times -1. Sine of pi is what? It's the y-coordinate. It's 0. So that goes away. That's very convenient. It's almost like they chose really convenient numbers. And I think it's because they did. By the way, you can also come up here. This is where pi halves is, at the top of the circle. And that's how you can see that the sine of pi halves, that's the y-coordinate, is 1. And the cosine of pi halves, which is the x-coordinate, is 0. All right, now let's clean this up. So what do we have? We have a minus b equals 2. And then if we multiply this negative through, we get minus 2a plus b equals 5. All right, so those are our two conditions. And, well, now we need to solve for a and b. Now, I like to do it by combining. Combining in such a way we get cancellation. If you like substitution, good for you. Do it. Do what makes you feel comfortable and you can carry out correctly. Because we want you to, first off, feel comfortable. Math should, maybe it makes you challenged, but it shouldn't make you uncomfortable. You should develop a comfort with mathematics. And the other thing is, math is flexible in many cases. There can be multiple ways to approach a problem. Do the one that works for you. So, for me, I like to combine, and I can see right away that the b's are going to cancel it. They're set up in a beautiful way, just right to cancel. So, combining, we add these up. The b's go away. A minus 2a is negative a. 2 plus 5 is 7. So that tells us that a has to be negative 7. All right. Well, so if a is negative 7, what does that say? Well, negative 7 minus b equals 2. So if we swap the b and the 2, that tells us that b has to equal negative 9. All right. Well, so those are our values for a and for b. Now we know a and b, we're basically home free. So we're ready to answer our question. Why? Because we now know that in general s of t is equal to minus 7t sine of t, and then minus 9 cosine of t. Because now we know the values for a and for b. The last thing is, what would be the position, and that's the s of t at time pi 4. So the answer would be s at time pi over 4. So we plug in pi fourths. So that would be minus 7 times pi over 4 times sine of pi over 4. Do you remember what sine of pi over 4 is? It is square root of 2 over 2. Then minus 9 times cosine of pi over 4, which is also square root of 2 over 2. And you can try to clean things up a little bit, but there's really not much you can do here. So we'll just live with this rather strange looking minus 7 pi root 2 over 8 minus 9 root 2 over 2. And, well, it is what it is, right? Sometimes the numbers can look strange, but that's all right. The process is good. All right, good. Thanks for coming and doing some practice. Keep doing the practice. You're getting better. And I know it doesn't always feel like it, but that's what happens. You know, your progress might seem slow when you look at it day by day. But when you look at it over a long term, you're like, wow, you know, I am getting more comfortable. So keep doing that practice. You're great and you're getting better. It's amazing. All right, see you again.